Chapter 1, General Definitions. First, mass. The unit of mass is kilogram and is the quantity of matter in a body. So, of course, the larger the mass, the greater the force required to start or stop this body in the same distance. Force. What is a force? Force is a push or a pull, and in the unit is measured in newtons. Force is a push or pull that which causes or tends to cause a change in a motion of a body. As we know, there are 4 forces acting on an aircraft in flight, pushing or pulling in different directions: lift and weights, thrust and drag. Now the difference is weight. The unit for weight is newton and not kilograms. So weight is a force due to gravity and is measured in newton, and this force is equal the mass in kilograms multiplied by the gravity. This is the acceleration due to the gravity is constant, which is a value of 9.81 meters per square second. So 1 kilograms of mass weighs 9.81 newtons. So if the mass of a Boeing 737 is 60,000 kilograms, and as we said, this force is equal mass per multiplied by gravity, it is necessary to generate mass 6,000 kilograms multiply 9.81 meters per square second, and it gives us the force in newtons necessary to counteract to lift the Boeing of so we need 588,600 newton of lift force. Now, center of gravity is the point through which the weight of an aircraft acts. So this is the aircraft, center of gravity is here, so the weight acts from here. And in flight an aircraft is said to rotate around this center of gravity. As we all know, the CG of an aircraft must remain within certain forward and aft limits for reason of both stability and control. Now, work is measured in joule. So work is a force, and a force is said to do work when it moves the body in the direction in which the force is acting. So the amount of work done on a body is the product of the force applied to the body and the distance moved by that force in the direction in which this force is acting. If a force is applied and no movement takes place, no work has been done. There was a force of certain newtons, there was no movement, so there is no work. So 0 joule. But for example, 10 newtons, no movement, 0 joules. So let's say work equals force multiplied by distance in meters. If a force of 10 newtons moves a body 2 meters along its line of action, it does 20 meters of work. So 20 newton meters of work. 10 newtons multiplied by 2 meters equals 20 newton meters. A newton meter is the unit of work and it's called joule. So a joule is a newton meter. So 20 joules. Now, power, the unit is watt, and power is simply the rate of doing work. So 10 newtons moving this 10 newtons move a mass 2 meters, but what's the rate? How long does it take to move this this mass 2 meters? So power watt is the work. So newtons multiplied by the meters, so force multiplied by distance over time in seconds. So as we said, a force of 10 newtons moves a mass 2 meters in 5 seconds. Then the power is 4 joules per second. A joule per second, a joule second, is called a watt, and the unit, this is the unit of power. So in this example, it's generating 4 watts. Energy. The unit of energy is still joule. Mass has energy if it has the ability to do work, so to move a mass a distance. In other words, a mass has energy if it has the ability to do some work. So if this mass coming to rest has the ability to move certain distance another mass. So the amount of energy a body possesses is measured by the amount of work it can do, how far it can move a mass, a body in coming to rest. So it's measured in joules. Similar, kinetic energy, still in joule. So the joule is the unit we use to measure work. So how many meters a certain force is moving a mass. Kinetic energy is the energy possessed by mass because of its motion. A mass that is moving can do work in coming to rest, as we said before. So that's kinetic energy. So in coming to rest, this mass can do work. So it can move a body, or it can do some work, can move a mass or a body in a certain distance. So the formula for kinetic energy is half the mass multiply square of speed. So the mass is as usual in kilograms and speed in meters per second. So the kinetic energy of a 1 kilogram mass of air moving at 52 meters per second, 100 knots, is 1,352 joules. So it possesses 1,352 joules of kinetic energy. So usually, approximately, the conversion of meters per second and knots is the meters per second is half knots. So for example, approximately 1 meters per second is 2 knots, or 5 knots are 2.5 meters per second, or 100 knots are 50, in this case 52 meters per second. So as we can say here, this is the mass, half of the mass, so multiplied by 0.5 plus square of speed, 52 meters per second multiplied by 52 meters per second, it gives you the energy in joules. As we said, joules is the unit we use to measure a force, the unit we use to measure work. So let's go back here. From the above example, it can be seen that doubling the velocity will have a greater impact on kinetic energy than doubling the mass, because velocity is squared. So a body has a certain mass and it's moving. If you double the mass, it gives you a value, keeping the same speed. If you keep the mass and double the speed, it has a greater value and greater joules at the end. So a mass of air of, for example, 1 kilogram, 1.225 kilograms is moving, let's say, at a 100 knots, so 52 meters per second. It has kinetic energy of 1,352 joules. Newton's first law of motion. A body will remain at rest or in uniform motion in a straight line unless acted on by an external force. To move a stationary object or to make a moving object change its direction, a force must be applied, of course. Now, inertia is the opposition which a body offers to a change in motion. Inertia is a quality, but measured in terms of mass, which is a quantity. The larger the mass, the greater the force required for the same result. So a large mass has a lot of inertia. So if there is a bicycle coming towards you at 30 kilometers, for example, you can stop it with one hand. But if there is a truck moving to you at the same speed, so it's not going faster, it's not accelerating, it's been launched, and when you stop it is at 30 kilometers, so not that fast, that has larger inertia, so it needs a stronger force to stop a truck than to stop a bicycle for the same going at the same speed, because of its higher mass. And of course, inertia refers to both stationary and moving masses. So you need more force to move a stationary object, for example, a truck, than a small car. Both stationary, both with the same value of the same amount of friction on the ground. So let's not take that into account. So to move a truck, you need to break that inertia, you need a greater force. So that's still called inertia. That's why, for example, to start moving a larger body, for example a Boeing 747 from a state of rest, you're gonna need more power to start moving the airplane, and once it's moving you can reduce power and it will continue moving with less power now. So the problem was breaking the initial inertia of that body, and once it's moving you can apply the correct force to keep it moving at the same speeds. But if you need, for example, let's say 50% of N1 to make it go 30 knots of ground speed. This is just an example. To make it move from a state of rest, you may need a larger force, so let's say 60% of N1. So these values are just an example, they're too high, of course. So you need 60% of N1 to break the initial inertia, and then those, let's say 50% of N1 to make it accelerate and continue to 30 knots ground speed, for example. So Newton's second law of motion: the acceleration of a body from a state of rest or uniform motion in a straight line is proportional to the applied force and inversely proportional to the mass. As we said, the acceleration is proportional to the applied force. The more the force, the more the acceleration, and inversely proportional to the mass. So if the force stays the same and the mass is higher, there is less acceleration. So the higher the mass, the less the acceleration, given the same force. Velocity, as we said, is measured in meters per second, and it's the rate of change of displacement. So the rate of change in movement. How many meters on how many seconds? 1 meter in 1 second, 2 meters in 1 second. Now, acceleration is meters over, unit is meters over squared second. So meters per second is the rate of change of velocity. So a force of 1 Newton acting on a mass of 1 kilogram will produce an acceleration of 1 meters over squared second. That's the acceleration. So we can say acceleration equals force in Newton over mass. So for the same mass, the bigger the force, the greater the acceleration. For the same force, the larger the mass, the slower the acceleration, as we said before. The larger the mass, the slower will be the acceleration, given the same force. Let's make another example, more realistic. Boeing 737. Let's say 30% of N1 will be enough to let the airplane accelerate to a certain speed. If the airplane is at full maximum takeoff weight with the same force generated by the engines at 30% of N1, the acceleration now will be slower, because the mass has, let's say, doubled. No, not doubled, but it has increased. Now, momentum. The unit is mass multiplied by velocity, kilograms multiplied meters per second. Momentum is the quantity of motion possessed by a body. The tendency of a body to continue in motion after being placed in motion. So if you push a truck, that's its momentum. Is mass multiplied by the velocity in meters per second at which I stopped, let's say, pushing this truck. As an example here, a body of 10 kilograms of mass. I finish pushing at when I reach a speed of 2 meters per second, and that has 20 kilograms multiplied meters per second of momentum. So at the same velocity, a larger mass has more momentum than a small mass. Okay, so same example, if I accelerate a truck and a bike at 2 meters per second, and then I leave them, the track has more momentum. So that's basically it. Newton's third law: every action has an equal and opposite reaction. If a force accelerates a mass in one direction, the body supplying the force will be subject to the same force in the opposite direction. I can do the same example here. If I try to move this, if I push this track, I will have same force, of course, applied to the opposite direction in which I'm applying the force. I'm trying to move this track forwards. I will have it will apply a force backwards in my hands. So this ends the definitions of chapter 1. We have a glossary here. Airfoil, what is a body? So shapes as to produce aerodynamic reaction to normal to the direction of its motion. Aft means to the rear, back or tail to the aircraft. Air brake, any device primarily used to increase drag of an aircraft wheel. Ambient means surrounding or pertaining to the immediate environment. Amplitude is the largeness, the width, the range, the extent of repetitive movement. Attitude is the nose up or nose down orientation of the aircraft relative to the horizon. Boundary layer, the thin layer of air adjacent to a surface in which the viscous force are dominant. Buffeting, an irregular oscillation of any parts of an aircraft produced and maintained directly by an eddying flow, and so on. So we can refer to this page every time we don't know any words or any definition. Is pretty long, so it's better not to discuss all of them. And as well a list of symbols. So this means proportional to, and this means is approximately equal to. So this is proportional to.